force method. I really don't want to find all 24 Hamilton circuits. With a computer, it'd be a piece of cake, right? But by hand, I'm thinking, I don't want to find all 24 and add them up. I just need a good answer. I'm thinking, here's a nice story that would go with this graph. This might represent cities, and I can go from one city to the next. The numbers might represent the cost of airline tickets because they're far apart. I'll fly. Now, I don't know, I guess we could say it's in hundreds of dollars. That'd be kind of expensive for tickets. Maybe in tens. 30, 70, 30, 40, 150. And I want to go to every city and go back home, but maybe I don't want to look at it and study it so much that I come up with the absolute cheapest flight. But I can do something else and get a good flight. And I'm thinking airline flights, it doesn't have to be airline flights, but you know, you all have had some shopping experience. And you like to get the best deal? Does that always happen? Probably not. But you want to get a good deal, even if it's not the best. Well, we have another technique we can use to get a good deal. Might not be the best deal. We have another method for finding a good Hamilton circuit. Even if it is not the best Hamilton circuit. It's called the nearest neighbor method. This is the nearest neighbor method. The nearest neighbor method is just what the name implies. You're going to go, you'll start at a vertex, and you go to the closest vertex to that one. Take care of business at the second one, whatever the errand might be. Then you go to the next closest one that you haven't been to. I'm going to draw this graph again, the same one I had previous, the same numbers. And we'll do the nearest neighbor method. See, A to E was 15. A to B is 9. B to C is 3. D to C is 7. E to D is 3. E to B is 8. A to D is 10. I missed a line, didn't I? Oh, I'm going to scratch that out just because it's hard to tell which one it's next to. I'm going to write it a little bit lower. A to D is 10. E to C is 12. A to C is 4. B to D is 19. going to start at C. I can start with whichever one. In fact, something you could do is do nearest neighbor from each dot. Start at a different one each time. Look and see which one was the best out of the ones you generated. Since it's a circuit, you don't have to start. So let me explain it. Let me show you with an example. I'm going to start at C. C to B is 3. C to A is 4. C to D is 7. And C to E is 12. Go the smallest one, the nearest one. I'll go C to B. From B, I could go to D, E, or A. We'll take the smallest one. C to A is 9. C to E is 8. B to A is 9. B to E is 8. B to D is 19. We're going to go to E. After I go to E, I have A and D left. E to A is 15. E to D is 3. Well, we're going to D. This will force me to use A to D, that's 10. And then from A, I have to go back to C. So using the nearest neighbor, starting at C, we have C, B, E, D, A, C. Then they're going to ask you to find the cost. 3 plus 8 plus 3 plus 10 plus 4. 6 plus 8, that's 14. 14 plus 14 is 28. It is quite possible that had I started at a different vertex, I would have gotten a different answer. Let's redo it and start at E. I'm going to draw a new picture. Same graph. So the weights, again, I'll put those in, same weights. See, A to D was 10. E to C is 12. B to D is 19. E to B is 8. And A to C is 4. I'm going to start at E. So from E, the shortest one, E to D. From D at this point, so I'm not going to A, I'm going to C at 7. From C, I could go to B or A. Well, we're going to go to B. This will force it A and then to E. So I get a different answer. And the weight of this one, let's see, 10, 13, 22, 32, 37. E, D, C, B, A, E. I got 37 when I added that.